Our first speaker this morning is Joy Kitson from the University of Maryland at College Park. Her field of study is computer science. She's done 2 practicums, one at Oak Ridge National Laboratory and one at Los Alamos.
Good morning, everyone. I want to preface with this talk by saying I'm not an epidemiologist, I'm a computer scientist, so I'll try to focus on those aspects of the work. But first, to start off, I want to provide a little bit of historical context for the work I'm doing. And that starts by looking at the question of how well do we manage infectious diseases currently? And if we take the longer-term perspective, well, in the last century and a quarter, we've made a lot of progress in that respect. On the left, we have a plot of the deaths due to infectious and non-infectious diseases over the course of the century and a quarter. And as you can see, we have had a dramatic reduction since 1900 of that. And that's due to a lot of innovations such as antibiotics, vaccines, and improvements in sanitation. However, if we look at the current state of things today, there's still a lot of work to be done. Obviously, we all remember the height of the COVID-19 pandemic, and there's a variety of other infectious diseases that continue to pose a major problem today between HIV/AIDS, malaria, and the various infectious diseases that cause pneumonia-related deaths. So this begs the question, how can we improve our response to new outbreaks of these diseases? And one potential tool in our toolbox is computational modeling. When we identify the outbreak of a new disease, policymakers generally seek to explore a variety of different interventions that they can undertake to slow the spread of that disease. However, it's hard to know a priori how effective any potential intervention might be, especially because in the early stage of these outbreaks in particular, there tends to be a lot of uncertainty in the ground truth of what's going on. And that's despite the fact that early interventions can have outsized impacts on the trajectory of an outbreak. And that's especially important to be able to model these because there's some lag between when we impose an intervention, when it starts having an effect in reducing cases, and when we would actually be able to detect that effect, when people start showing up with symptoms, when they start becoming hospitalized, and so on and so forth. So this kind of begs the question of how well did we do at this for COVID-19? And despite the mountain of effort that's gone into modeling the pandemic, there's still some significant limitations to the models that are currently out there. Up here, I have a plot of the observed case data put out by the Johns Hopkins University in black, alongside a few select 4-week predictions put out by the US CDC's COVID forecasting hub ensemble, which outperforms any individual model. And the highlight here is that the existing models often fail to predict when new waves will begin and end. And it's worth noting that these models are still quite useful for guiding resource allocation because they can predict the hospitalizations and deaths a bit more accurately than cases. But that does still mean there's significant work to be done here. So what potential approaches can we consider for improving these models? One potential class of application that has shown some promise is what's called agent-based models, where we directly represent individuals in an artificial synthetic population, and we can directly model changes in their behavior that policymakers might target with a set of interventions. And this makes them very useful for comparing a range of different potential options policymakers might want to consider. However, the current agent-based models out there generally fall into 2 categories. One, models which are quite scalable but have relatively simple assumptions about how people behave, particularly in the absence of these top-down public health interventions. And then there are also some more detailed models that generally can't scale beyond around 1 million people or so. And so what we really want to be able to develop is an agent-based model that can capture more detailed assumptions about how people might behave on a national scale. So one direction I've taken in pursuing this goal is to start by improving the underlying scalability of this class of model. First simulation I worked with is called LIMOS. We take as input a visit schedule specifying where discrete people in the synthetic population are at given points in the day. These populations in practice are generated to match a variety of distributions in census data, commute flows, et cetera. And once we have that visit schedule, we distribute it across all of the visits in the simulation. And we can update that schedule to reflect the impact of a certain set of interventions, such as school closures, as shown here. And then once we've distributed those visits, we compute a discrete event simulation at each location in parallel to determine who's at the same location at the same time. And then finally, we can sum up all those contacts across the entire simulation to determine the probability that any given agent becomes infected. So the initial implementation of this simulation had a few different scaling challenges that we noticed, which we tested on Perlmutter on this data set of around 9 million people. First one that we identified was some rather significant load imbalance. On the left here, we have a plot showing where we're spending time on individual processes in the simulation. White is idle time, and these colored sections represent time we're spending in different phases of the simulation. And we were able to develop a static load balancing scheme. Essentially, which starts by sorting all of the locations in the population by their zip code, essentially treating that as a space filling curve, and then computing slices within that sorted data in order to minimize the load on a given partition. The reason why we might want to take this approach over something like graph partitioning is because this is much quicker to compute for a given set of processes that we want to run on, and that makes it much easier to adjust the partitioning when we're scaling to different node counts. We do still have some remaining heavy processes. Generally, these correspond to processes that have a single very busy location that receives a lot of visit messages. But overall, we do see a pretty significant speed up from applying this intervention or this optimization of around 5.5 times on a single node and 3.5 times on 32 nodes of Perlmutter. The second problem we noticed in our implementation is that the initial runtime of the discrete event simulation actually decreased over the course of the simulation, despite the fact that cases were increasing. And this was rather counterintuitive because you expect the time we spend in the discrete event simulation to correspond to the number of contacts, and those number of contacts correspond to the number of new infections, very roughly. So we realized that if we essentially skip computing that discrete event simulation on any location that doesn't have any infectious people present, one saw the expected trends that we had seen where the time in this phase corresponds to the slope of new infections, but we also dramatically reduce the time we spend in that phase overall. And this results in about a 65% speed up overall on a single node. Final issue we noticed was some inefficient communication patterns in the visit distribution at the start of the simulation. Essentially, we have at the top here the amount of time we're spending in different phases over the course of 3 iterations of the simulation. In blue, we have the time we're spending in the visit schedule exchange, and in red, how much time we're spending on the discrete event simulation. Obviously, as you can see here, the bottleneck was sending those visit schedules. We had initially decided to store them on the processes that have the corresponding people because that allowed us to quickly update those schedules in the presence of interventions that are applied to individual people. However, that did impose significant communication costs to send those visit schedules over to the processes which have the location data. We were able to completely rework the algorithm in order to store the visit data on the processes with the corresponding locations, which allowed us to only send updates to people's disease states as opposed to their entire visit schedule. And then we were able to compute changes to the visit schedule just by knowing which people were going to be infected by those changes, because we have the information about their current state in order to compute those updates. And we were also finally able to batch those. This resulted in around a 2.4 times speed up on a single node of Perlmutter, and combining all these optimizations gives us a total of around a 31 times speed up over our initial implementation on one node, and about a 5.8 times speed up over our initial implementation on 32 nodes. We also tested our implementation on a few different larger data sets, in particular this California data set of around 3.5 million people. As you can see here, we get pretty consistent strong linear scaling on these larger 3 data sets. And in particular, we are able to achieve a speed up of around 2 times over the state of the art, a simulation called episyndemic, when running on about 2/3 as many cores, as you can see here. Okay, focusing back on the behavior element, we implemented a dynamic behavior model in another simulation called EpiCast, developed at Los Alamos. Here, the model we implemented is this coupled contagion model, where we have fear of the disease spreading alongside the disease itself and motivating agents to adopt protective behaviors. Essentially, that fear is spread by contact with agents who have symptoms, who are already afraid, or by conventional broadcast media in areas that have relatively high fear already. And then that fear can be lost through contact with agents who have recovered from a symptomatic infection over time, or broadcasters in areas with falling cases. And for this, we're essentially adapting an existing ODE-based model to the agent-based context. So our initial implementation of that model suffered a pretty significant slowdown, primarily due to the increase in number of agents that are spreading something. In particular, we have about an order of magnitude more agents that were spreading fear than the disease itself, and that significantly slowed down the simulation, as you might imagine. We were able to overcome this by entirely reworking the transmission kernel for those 2 contagions. Initially, we were computing those transmissions pairwise, and first checking if there is the potential for spread, and then for every pair that there is, computing that probability. We were able to rework this by essentially binning the counts of agents in different states. And we can then make a single pass to compute the counts in different contexts, which are analogous to locations in the previous simulation I discussed. And then once we've made that first pass to compute those counts, we make a second pass to compute the transmission probabilities. And overall, this results in an 8 times speed up over that initial implementation, which actually brings us a little bit faster than the initial full version of EpiCast that we were comparing against. And when we apply this optimization to EpiCast itself, we also see about a 1.3 times speed up as well. And all of this work allowed us to run these simulations of disease spread with and without the fear-induced behaviors for the entire US in under an hour on a system at Los Alamos. And you can see that we have very dramatic differences in the disease curves. In particular, we see a lot more variation in the state level progression of the diseases in the fear-based simulation, as well as the emergence of those multiple epidemic waves that we've observed in real life. I just want to close out by thanking the many collaborators that I've been lucky enough to work with over the course of this program, my lab at the University of Maryland, team at Los Alamos, and a team of epidemiologists from the University of Virginia, as well as all the help from Krell staff. Thank you.